Good morning to everyone. This is Shubhangi Rao. I'm working as an assistant professor in MLR Institute of Technology. And here I am teaching in Department of EEE and taking subject EMF. And today we are going to discuss about BIOT-SAVART'S law. So this topic belongs to the third unit of EMF subject, magnetostatistics. And this is the introduction of BIOT-SAVART'S law. The BIOT-SAVART'S law is an equation which describes the magnetic field which is generated by constant electric current, or you can say direct current. It relates the magnetic field to the magnitude, direction, length and proximity of the electric current. This law is consistent with both Ampere's circuital law and Gauss theorem. Gauss theorem is same which we have discussed in the electrostatistics. Another point which we must know is the BIOT-SAVART'S law is fundamental to magnetostatistics, playing a role which is similar to Coulomb's law in electrostatistics. Next, we'll move. So, this is the arrangement in the diagram you can see which we need for understanding BIOT-SAVART'S law. We are considering here a conductor which is carrying a direct current. This is the conductor and it carries direct current I, and a steady magnetic field will be produced around it. As we know that current carrying conductor produces magnetic field. So, here it follows the same. We have a conductor which carries a direct current and a steady magnetic field is produced around it. This BIOT-SAVART'S law allows us to obtain the differential magnetic field intensity. This is magnetic field intensity which is given by H, and when we write D it becomes differential magnetic field intensity. So, by using BIOT-SAVART'S law, this differential magnetic field intensity can be found, and this magnetic field intensity we will obtain at this point P due to this differential element which we are going to consider at this conductor. Right, let's move further. So, what we are doing here, we are considering a small differential length dl. So, this differential current element becomes I dl, and this differential current element is a very small part of this current carrying conductor. This is point P, it is at a distance r from the current carrying conductor, and at this point P we are going to find magnetic field intensity, differential magnetic field intensity. Here you can see this angle theta. This is the angle theta which is formed between this current carrying conductor and the line joining this line, this current carrying conductor and this point P. Right. So, this is the arrangement. Now, what about BIOT-SAVART'S law? What is BIOT-SAVART'S law? BIOT-SAVART'S law states that the magnetic field intensity dH which is produced at this point P due to this small differential current element IDL can be given by, the first point says it is proportional to the product of current I and differential length IL dl. So, this can be written as IDL. Also, it is proportional to the sine of angle between the element and the line joining point P to the element. That means this becomes sine theta. And third point says that it is inversely proportional to the square of the distance between, it is inversely proportional to the square of the distance r which is between this point P and the element. So, we can write it as 1 upon r square. So, when we combine these 3 points, we get dH is directly proportional to IDL sine theta upon r square. This proportionality sign can be replaced by equal sign, and we can write K in place of proportionality sign, and this formula becomes dH is equals to K IDL sine theta upon r square, where K is the proportionality constant and its value can be written as 1 upon 4 pi. Now this formula becomes ideal sine theta upon 4 pi r square. Right? Here, this equation can be expressed in vector form. This dl, let us consider this is magnitude of vector length dl, and ar is the unit vector in the direction from differential current element to point, means this is ar. So, from the rule of cross product, we already know that dl cross ar can be written as dl ar sine theta, which is dl sine theta. Now, if we go back to equation number 3, this equation number 3 says ideal sine theta upon 4 pi r square. It is nothing but this. So, this can be written as dh is equals to ideal cross ar upon 4 pi r square, and the unit will be ampere per meter, where ar is the unit vector and it can be written as r upon mod r, or we can say vector r upon mod r. And if you see this equation, dh is equals to ideal cross r upon 4 pi r cube, because we are putting r upon this mod r in place of this ar. So, this becomes r upon, here it becomes 4 pi r cube. So, these two equations, equation number 4th and equation number 5th, these are the mathematical form of BIOT-SAVART'S law. And if we put integral sign on both the side, or here also same thing, so we get the BIOT-SAVART'S law in integral form. So, this equation becomes integration of ideal cross ar upon 4 pi r square. So, both the forms are correct. This is differential form and this is integral form. So, this is BIOT-SAVART'S law. Now, we can see BIOT-SAVART'S law in terms of distributed sources. Here we can see one diagram which shows surface current density. So, we are considering a surface here which is carrying a uniform current over its surface. Right here in the diagram you can see. So, we can say the surface current density here is denoted by K, and it can be measured in terms of ampere per meter. So, when we want to write uniform current density, the current I in any width B can be written by I is equals to KB, right, where this width B is perpendicular to the direction of current flow, right. And also because we are talking about surface, so we have to consider this ds. So, this ds is the differential surface area considered of a surface having current K. Then this term ideal becomes KDS for surface current. If we want to take volume, then this ideal becomes J dV, where J is measured in ampere per meter square, right. So, now if we want to write final formula for surface current, this is for surface current, this is for volume current, and the previous formula which we have seen, that is for line current, because we are considering a conductor which is having current I. So, here for surface current, magnetic field intensity is given by surface integration of K cross ARDS upon 4 pi r square. The unit is ampere per meter, and this becomes H is equals to J cross ARdV, integration of J cross ARdV upon 4 pi r square. So, basically we have got these three formulas, one for line current, another for surface current, and third is for volume current. So, this was about BIOT-SAVART'S law. Hope it is clear. Now, we will discuss about the applications of BIOT-SAVART'S law. Applications means by using this formula of magnetic field intensity, by different arrangements we can find out magnetic field intensity. So, first case we are going to consider is magnetic field intensity due to infinite long straight conductor. So, as its name says, it is a conductor, straight conductor which is infinite in length, means its limit can be considered as minus infinity to plus infinity. So, we are considering an infinite long straight conductor which is along z axis, and as we are discussing BIOT-SAVART'S law, we are talking about magnetic field intensity, we will say a current passing through the conductor, it is a direct current of 1 ampere, and with this long current carrying conductor, infinite long current carrying conductor, we are going to find magnetic field intensity on this point P, which is at a distance r from current carrying conductor, right. So, similar to the previous definition, here also we are going to consider a small differential element at this point, okay, and the length of this differential element from origin is given by z, and we are writing z, az, because these are all directional quantities. So, az is unit vector for z. So, this ideal becomes, in place of dl we are putting dz az, because it is in z direction. Similarly, if we consider this conductor in x direction, it becomes I dx az ax, and if you consider this conductor in y direction, it becomes I dy ay. Now, we will see further. Here we have one more distance, this we need to find out this expression also. So, this R12, this is between point 1 to point 2, this is point 1, this is point 2. So, this point minus this point. So, R12 is given by minus ZAZ plus RAR. Now, we can find out unit vector AR12 also, which will be given by R12 upon mod of R12. So, R12 just now we have written RAR minus ZAZ divided by mod of this distance. So, when we take mod of this, it becomes under root of R square plus Z square. And when you simplify more, when we put that into the main formula, it becomes dl cross AR12 cross product, and we get R dz a phi, right. So, when we are obtaining this R12, when we are obtaining this cross product, this R12 is neglected, right. Now, again we will consider its, we get ideal cross AR12 and we are getting IR dz a phi upon under root of R square plus Z square. Now, see the formula which we got from BIOT-SAVART'S law, dH is equals to ideal cross AR12 upon 4 pi R square 12. Now, we will put all the expressions which we have got previously. In place of this, we are putting IR dz a phi, and in place of R12 square also we will be putting the expression, and we get IR dz a phi upon 4 pi in bracket R square plus Z square to the power 3 by 2, means we are getting this from this, right. So, this is the formula which we have taken as equation number 5. Now, we want to find out total field. The previous formula which we have seen, this one, this is basically DH, differential form, but we need to find out total magnetic field intensity. So, we will integrate this equation number 5 at both the sides, left hand side, right hand side. So, this becomes integration of DH, and if you notice, now we need to put the limit, because the differentiation integration is with respect to dz. So, the limit, because we know the conductor is along z axis or is in z axis, and the limit is, because it is infinite length current carrying conductor, the limit is from minus infinity to plus infinity. Similarly, we will put here minus infinity to plus infinity. So, now this formula is this. Now, we need to make some assumptions, or we will consider few more expressions. We will put z is equals to r tan theta. Now, if you square both the side, this z square becomes r square tan square theta, and if you differentiate it, this dz becomes r sec square theta d theta. So, these things, these expressions we need to put in this formula. So, when we put it, we will get this expression. In place of z we are putting, in place of z square we are putting r square tan square theta, in place of dz we are putting r sec square theta d theta. So, we get this expression, we get this rr will become r square sec square theta, this dz has become d theta, a phi upon 4 pi r cube sec cube theta. Now, if you notice, Now here we have theta in place of z. So according to this, the limit will also change. So this minus infinity becomes minus pi by 2 and this becomes pi by 2. Now we will further simplify it, and after simplifying we get 1 upon 4 pi r integration of minus pi by 2 to pi by 2 cos theta d theta a phi. On simplifying this further, we finally get the formula I upon 2 pi r a phi ampere per meter, right. This is the formula for H, means magnetic field intensity. This is flux density. As we know, B is equals to mu H. So in this formula we can put H and we get mu I upon 2 pi r a phi Weber per meter square, right. So this is the formula we were looking for. This is the magnetic field intensity due to infinite long current carrying conductor, right. And if you notice in this formula, it depends only on r. It is not having phi, it is not having z, only r is there, right. Also the direction of H is tangential because here we have a phi, right. So this direction is going into the plane of the paper at point P. So this was the first application of BIOT-SAVART'S law. Let's see another application. Now we will find out H at the center of circular conductor, right. So to do that, we have this arrangement. Here we have a current carrying conductor which is arranged in a circular form, and here current is flowing through it, constant current, and due to this arrangement we need to find out field intensity at center of this circle. This point is located at the center of this arrangement. Similar procedure, we need to consider a small element dl on this conductor which is circular in shape. This is angle theta, this distance is r12 and this is I dl, right. So again we need to use the same formula, dH is equals to I dl cross AR upon 4 pi r square. So I dl cross AR12, this is the formula, this is the expressions which we are getting. This is I dl sin theta an, right. What is an here? This is the unit vector which is normal to the plane which contains dl and AR2, right, or we can say it is normal to the plane in which this circular ring is there, right. Now this is the formula, dH is equals to I dl cross AR upon 4 pi r square. We need to put what we have already obtained. So I dl sin theta an upon 4 pi r square. Now we will further simplify it, we will integrate it both the sides. So we get I sin theta an upon 4 pi r square integration of dl. Now because it is a circle, right, now we want to find out the total length. We know the circumference of circle is 2 pi r, where r is the radius of the circle. Now we put it into this formula and we finally get I sin theta upon 2r an, right. This ideal is tangential to the circle and r12, that is why the angle theta must be 90 degrees. So when we put sin 90, we get 1 and finally the formula is I upon 2r. So magnetic field intensity due to a circular current carrying conductor will be given by I upon 2r an, where an is the unit vector, its direction is perpendicular to the plane of the current carrying conductor, and from this formula we can also find B, flux density. B is equals to mu H. If we want to find out this in free space, this mu becomes mu naught, and B is equals to, we get mu I upon 2r an Weber per meter square. This was the second application of BIOT-SAVART'S law. Third application is we can find out magnetic field intensity on the axis of circular loop. What is the meaning of that? See this arrangement here, the circular loop is in xy plane, okay, its center is along z-axis, and in this circular ring usually the current is flowing, and due to this we need to find out field intensity on point P, which is located on z-axis, right. So, this is the point where we are finding out field intensity due to this circular loop. Similar procedure, we need to find out dl, okay. So, we will consider a cylindrical coordinate system. So, the dl is given by dr ar plus rd phi a theta a phi plus dz az, right. Then we need to find out ideal also. Ideal will be given by IRD theta a phi, just like previous case. We will find out AR12, which gives R12 upon mod of R12. Now we can find out R12. The distance between these 2 points means this point x coordinates minus this point. So this becomes minus RAR plus ZAZ. Mod of R12 means under root of R square plus Z square. So finally we get this formula for AR12. Now we find this product dl cross AR12. We get ZR d phi a phi AR plus R square d phi AR, right. Next, we will put this expression into this formula. Then next step is to integrate it, right. The limit is phi, this is with respect to phi. So, the limit will be put in as 0 to 2 pi, 0 to 360. Next, we will further simplify it. We will write it in this simplified form, right. This first integral term will be proven to its value will be 0 due to the radial symmetry. So, only second term will be considered. We further elaborate it and we get this term ZR d phi upon R square plus Z square AR, and the integral limit is phi is equals to 0 to 2 pi, right. Now we will simplify it. This is the first term which has become 0, right, and this is the integration for second term. So the limit is from 0 to 2 pi, right. When we further simplify it, it becomes I R square Az upon 4 pi R square plus Z square to the power 3 by 2. Then integration is with respect to d phi. The limit is again the same limit 0 to 2 pi. When you simplify it, we get I R square upon 2 pi Az upon 4 pi R square plus Z square to the power 3 by 2, right. On further simplifying, we get the formula in the simple form I R square upon 2 R square plus Z square to the power 3 by 2. And the unit vector is Az. Here we already know the small r is the radius of circular loop. Z is the distance of point P along the z-axis, means from that plane of circular conductor to that point the distance is Z, right. Now if that point P is shifted to the center of origin, center of the circular loop, means if Z becomes 0, means in place of this point, if this point is shifted here, means Z becomes 0. So we obtain this formula, Z will become 0, this becomes I R square upon 2 R square to the power 3 by 2, and this will get cancelled, and again R square cancels. Finally the formula is I upon 2R Az ampere per meter, right. So we discussed about BIOT-SAVART'S law. Also we discussed about BIOT-SAVART'S law for surface current, line current and volume current. Then we discussed about the applications of BIOT-SAVART'S law. 3 applications we discussed. Hope it is clear to everyone, and in case of any query, please write to us. Thank you very much.